iC-Haus, Integrated Circuits.
Hello and welcome to our today's webinar about smart inductive position sensing. I will introduce you a new chipset with a tiny footprint. My name is costs., and I'm responsible as a sales and applications engineer for encoder-related devices, especially interpolation ICs, and that also brings me together with magnetic sensing. I would like to introduce you today to an alternative method of taking a position, namely the inductive measuring principle. Now, our focus of today is on absolute position sensing, and I will try to explain what you, as an applications engineer, need to know about the different technologies. I will give you an overview of possible solutions and explain where the iC-GI22, our new inductive solution, ranks in terms of performance. Beyond the theory, in a second part, I will look at the hardware to give you a live demonstration on setting up operation, commissioning the sensor device, and to show how easy it can be for you to achieve an excellent measurement accuracy. And finally, at the end, we do have time for your questions. Now, initially, as an introduction, I would like to discuss some possible target applications. On the left side, you see this linear encoder, as well as this rotary encoder. They traditionally use either magnetic or optical sensing technologies. These devices operate in a sealed housing. The scanning is performed at a constant air gap. Now, interference can also be controlled so that the environment for the sensor is very convenient. The form factor is also more or less standard. The size 36 millimeters and also the 58 millimeters are quite common. Now, for setting up operations, this device is usually calibrated at the side of the manufacturer with a free selection of resources, meaning tools and complete procedures for automation. From the perspective of the IC designer, a fixed scale is actually suitable for such devices because the diameter is known and also the pitch can be defined. And that's exactly what we did. So we created a revised portfolio, namely this iC-PTH series of 6-channel motor encoders, which are used for speed feedback and also commutation. Now, the world changes if we look at other applications, for instance, AC servo drives or direct drive motors. You can imagine the diameter can get very large. Also, the robotics applications, they may ask for a larger inner hollow shaft. Now, the difficulty is now that the calibration must be done after mounting, and therefore it is a good idea to have a standard interface to do this, and also to have the standard tools for this. While we as an IC supplier support you with a graphic user interface to do exactly this task. So we have an interface to the sensor. From the perspective of IC design, we now have a flexible scale. The diameter can be different, and also the pitch. This has led to programmable system-on-chip solutions. For instance, the optical IC-PZ series is a reflective encoder which can be adapted to the scale and use. Same for the magnetic solution. The IC-MU series comes along with a bunch of different targets, so you can again change diameters. Now, if the sensor is externally, as it is the case for traditional magnetoresistive linear things, then you connect an interpolation device and build the system. You see, I'm getting towards the inductive solution. Again, the sensor is now externally, it's designed on the coils, and now with the help of a suitable front-end IC, such as the iC-GI22, plus a suitable interpolation IC, you can build the system. Now there are more applications out there. I don't like to cover this today. You can have to deal with any size and additional component qualification when heading for automotive applications, for instance. Let me spend some words on the device we are going to build, the position encoder. From the left to the right, so we have the sensor device here, called the transceiver, a channel that is usually just a cable, and outside of the receiver we have the PLC, which asks for a certain interface protocol. Now, it doesn't play a role what sensor principle is in use. Typically, each motion control sensor must evaluate multiple signals, for instance for position, for speed, and also for maybe a north marker. Even incremental system has one more channel to say where's the north direction. So if the sensing principle is optical or magnetic or inductive, it doesn't matter. Usually we do have a fine scale here on level 1, which is an incremental scale, and a second level 2 scale, which is raw, giving us an absolute information. Now, well, if you like to go purely analog, you can do so. The chip we suggest includes the required line drivers to go on the cable to the PLC, so you can go direct. Typically, if you ask for a digital interface, if it's a serial interface such as BIS or quadrature interface, ABZ output signal, then you will have a single processor in between taking care of this job. And that is a device I'm going to explain in more details also. Now, let me summarize what technologies are available. I'm starting here at the bottom. The magnetic on-axis solution is typically a Hall sensor, also an AMR angle sensor. So the Hall sensor is always a trade-off. You get some noise from the sensor, you may need to limit the bandwidth, but it's actually the smallest possible form factor to build such a device. Those are used for VLDC motors, for instance, or for HMI interfacing. Well, if you go off-axis, that is when the IC does not face the axis centrally anymore, but evaluates the pole wheel, for instance, then you get more input cycles and you can higher the resolution. It is also quite common to use magnetoresistive sensors for linear applications here, along with an interpolation IC. So GMR, gear tooth scanning, is not so much different, but here the energizing, the excitation now comes from a magnet on side of the stator, which is usually placed behind the sensor. Typically a GMR sensor does this job. Or modern devices, for instance the ICPVS, as a programmable horn line sensor, can also do this gear scanning. When you get to optical solutions, you may note that the line count is significantly higher. If it's reflective or transmissive, you benefit from a higher input resolution. Well, I mentioned here the 4096. Just as an example, it's definitely not the technology limit. You may have noted the gap in between, and that's exactly where inductive comes in. Now we have, again, a detector which is scanning the rotary target over its entire circumference. So this scanning is holistic, and that way we can eliminate alignment errors. And as you can see, the line count we detect is more or less in the range for magnetic off-axis systems. Let me explain in more detail how this does work. So we have a stator coil, which is an excitation coil. It is powered by the IC in a megahertz range. So we put in their energy, excitation energy. So this generates an electromagnetic field, which then hits the target. The target, that is the rotor here, that is mounted to the motor axis and rotates with it. Now you see these dark areas here, those copper surfaces are causing induction currents, so-called eddy currents. And induction is against the energizing, so it is disturbing the field we introduce to the rotor. Now you can imagine that this disturbance can be read out by specific coils here working as an antenna. So that's why we get a modulated AC signal telling us something about the position of those segments here. I'm showing here 4 segments only, but this can be any number. It's just a question of the size you can allow for the sensor design. Now, what do we different here? When we ask for incremental systems, it would be enough, but we are asking for absolute systems. So we added more coils in the center to read an absolute information. So this slave channel, we call it slave signal, we are reading an absolute signal providing us a starting position. So that way we can easily point into our incremental scale to initialize it. How does the circuit concept look like? So that's the iC-GI22. When you power it up, it restores its configuration from the external EEPROM, or if that's not there, you can link a microcontroller to play in and set up. It then powers up the oscillator, the driver circuit, providing the excitation energy to the external LC. So this LC components, they define the oscillation frequency. Our oscillator just provides the power to it. Now, on side of the receivers, we are getting this modulated, amplitude modulated input signal, and the job here is to get rid of the carrier frequency, and of course, we must do some signal conditioning. Why is that? Imagine you change the sensor design and also the air gap you install, and this in turn impacts the amplitudes and also the signal offsets. So the IC must condition the input signal. And finally, we have drivers to go outside, and here, on the side of the receiver, you would like to expect a controlled analog output signal with very low offset. And that is exactly what we do, doing this signal conditioning, employing an additional automatic gain control, we can go for a very stable output signal. The second channel, more or less fully the same. Well, maybe you have seen this small icon in here. That is actually an 8-bit digital converter. So this resolves our absolute signal, and we are then able to play it outside over SSI. This saves us components on side of the aberration circuit. Now, what are the key features? Let me summarize it. So we have 2 independent receiver channels doing the demodulation and the conditioning. Single frequencies you can allow, so that is the modulation frequency, you can reach up to 50 kilohertz. This in turn allows it for 90,000 RPM minimum if you would have a scale introducing 64 input cycles. If it's less, it's much more than that. Gain is adjustable, there's coarse and fine gain. Range is up to 200, that's a lot. The automatic gain control feature is independently for each channel. Signals are different in amplitude. And you have a precise offset correction, eliminating all the offset down to a few millivolts or less than a millivolt. Now, the adjustable coil driver powers up to 20 milliamps, and the whole chip is powered at 3 volt or 5 volt. It takes not much current, just 50 milliamps, maybe 20, and it comes in a very space-saving package. It takes just 5 millimeters. On the output side, you have the choice of the level. You can get 2 volt output amplitude, meaning differential amplitudes, 1 volt or 500 millivolt, and you can also input a center voltage if you don't like to have what the IC is offering, so as an input to allow tuning here. Now, if you go on the cable, we have the included cable drivers providing this industrial standard 1 volt peak-peak differential signal, what you then can terminate on side of the receiver with 100 ohm. The interpolation is an 8-bit interpolator, a vector tracking interpolation with 1 LSB accuracy. That's enough for our purpose. And it outputs SSI, including error and warning messages. You can mask those from the status information. iC-GI22 is embedded for automatic self-calibration on power-up from the external EPROM, and also as an iC-GI22 slave if you like to interface your MCU. Operation monitorings include loss of signal, oscillation failure, output short circuits, excessive temperature, and of course the RAM content, the configuration is monitored cyclically versus the CSC. You can mask all those status messages for the output. Now, what is the system concept? I already explained our sensor front end, doing the excitation, sensing, the demodulation, and the preconditioning, and of course some portion of monitoring. In the core, we would have a single processor which is in charge of analog to digital conversion, and of course dynamic error correction is a good idea to compensate any changes in the sensor front end. Imagine if your axis moves due to thermal expansion or load. The most important point here may be the input-to-output scaling. So this gives you the opportunity to do any line count on the input, and you can generate from this any output resolution. For instance, if you ask for a 2500 CPR incremental encoder, which is a decimal resolution of 10,000 increments, then you can use also a prime number on the input to generate this. No problem to do that. This processor monitors the signal quality. Maybe I should say it does condition monitoring. This information is very valuable, and it allows us to do something with it, to monitor if the accuracy in operation is maintained, and we can do the commissioning more easy. So this signal processor features some encoder interfaces. It's shown here. It can be BIS, SSI, ABZ, or commutation output. It works already standalone, so the absolute data output here is processed by this engine. So adding something here is an optional function, but I propose to do that. Why? So here it is easy for you to add service and supervisory functions, or if your customer is asking for more memory available to the BIS, for instance to store an electronic data sheet or so, you can do it on here. Same if you need a protocol conversion to any different interface protocol. So this would be done on this coprocessor, or I call it system processor. So this firmware is custom. It's a job of our customers to do that. Of course, we can support for the design in. Now let me look closer on the iC-TW29 proposed here as the signal processor. So it's an engine resolving the master channel, doing the rescaling for the outputs, and it already includes the engines we need in hardware, namely the BIS interface, so it just needs a transceiver on the side. And then you have this absolute data interface, which is able to process the GI data. Host processor, you see there's no EPROM anymore. In this case, we are replacing the EPROM by the host processor, so this is now more easy to configure it over the BIS, including the GI front end. Now, what we did is also to implement a command for automatic calibration. I will demonstrate it later on how this does work. So this allows us very easy on push of a button, or in this case, using a command to automatically calibrate our system, what saves a lot of time. And what I'm going to show you is how the quadrature signals look like. So I'm using this internal engine generating ABZ, and we will see how the jitter performance is here. Now, some words on our signal processor or encoder processor. Our inputs accept low-level, high-level signals. As a level shifter, we would have an external sensor providing a 2.5 volt in offset, common mode range. Signals up to 700 kilohertz can be processed. That's way too much. We don't need it here. But we need this feature for scaling. Input cycles can be adapted to the sensor in use. Now, the absolute data interface is able to read the SSI data with error warning and process it to initialize the absolute starting angle. Now, on the output side, we would have differential RS-422 drivers if you do a purely incremental system. In our case, we use BIS and ABZ in combination. And the resolution for ABZ can be very, very high, so this may not make use in combination with inductive, but you can do everything what is on the market, what is offered as an incremental encoder on the market. No problem at all, it's included here. UVW for motor communication, the sensor is absolute, no problem to output here the commutation signals. For the control, this interface is included, so this is profile compatible, and the chip also includes a simplified electronic data sheet saying something about the maximum allowed speed, resolution, and so on. Now for the controls, we could do a calibration on push of a button. In our case, we prefer a command, which is executed on the MCU. And the MCU here is linked over SPI. Memory is on chip. So this is an autonomous solution. Now, the most important feature here is this flexible scaling. We call it an electronic gearbox. So you can adapt it to any line count on the input to generate any line count, any pulse count on the output. Imagine if you would apply a scale featuring 16 input cycles and you would like to get 2,500 CPA on the output. This would result in a very crucial interpolation factor, but that's possible using this gearbox. Now, this brings me forward to performance. What I'm going to demonstrate today is actually a system design using 4 master periods, as already seen on the slides formulae. The sensor dimension is 39 millimeters, and I'm resolving from this 18 bits. Accuracy I will going to demonstrate is in this range. It's better than 0.1 degrees. And repeatability is something I cannot directly demonstrate here, but this is already measured, and it's, of course, a little bit better. Now, if you higher the input line count, you definitely can go for higher resolutions and better accuracy. Finally, where is it limited to? Actually, it is limited to the noise-free resolution offered by your ADC or by the interpolator. In our case, that is plus minus 80 arc seconds per input cycle, per segment. So this divides by the input line count, so you can easily go for 5 or 10 arc seconds accuracy. Okay, I need to speed up a little bit. Now, you may worry about the track requirements for the slave for initialization, but I can say you it's very easy here if you have just 4 master periods, very lousy accuracy required on the slave. But this hires up here. The more lines you have on the input, the more precise the slave track needs to be. The positive point here is if the size increases, also the accuracy of the slave track increases. So this can be done. A few facts on the total system. So it runs off 3.3 volt, takes 50 milliamps, and in our case allows up to 700,000 RPM. Total position lag is the summary of the front end plus the digital conversion. We are about 6.5 microseconds as the position lag, which is also compensated. So this is what we see, what you get on the output. Now, technology benchmarking, that is a question on everyone's lips, of course, so I need to speed up here. The traditional Hall sensor is limited due to the noise and bandwidth things, so it's hard to get devices which play better than 0.3 degrees. With the TMR at hand, we can reach this 0.1 degree target. Of course, when going off axis, we have more lines at the input, so those devices, incremental things, they can reach 80 arc seconds accuracy, roughly. The optical sensors, of course, they benefit from a much higher line count. So here it's more easy to reach high accuracy, also since the scale accuracy is way better. Now we have fit inductive in here, so it is in the same range as the off-axis Hall things, with a limited line count. And what I'm going to demonstrate here today is roughly at this corner here in a 13-bit accuracy range. Now, my demonstration setup. My device on the test is mounted to a drive with a reference encoder. There's a BIS chain playing over the reference data, and this is processed on my graphic user interface. Besides, I have the ABZ signals connected to a picoscope so that I'm able to see what is the jitter here. And I also look at the analog sine cosine signals using a, so to say, software-based oscilloscope, which allows us to show you a Lissajous figure. Now, what I will change is the air gap. So the setup is playing at 2.5 millimeters. I will change it, and I will also change the planar alignment. Okay, let's do some practice. I did not show this. When the sensor is this small, it's possible simply to align it visually over the holes. If it's larger, it's not an option anymore, but I can show everything here. So this is the rotary target mounted to our reference drive. The sensor PCB is here, connected to our evaluation circuit. So this is equipped with the GI22 plus the TW29 plus a controller allowing us some additional functions. So it's connected over the BIS connector to the screen here, to the GUI. And besides, I'm using the synthesizer to pick up the analog signals. Now, initially, I get some reading, but it's not yet absolute. It does not work. So I power up my drive, and now I have two choices. For instance, I could look at the comparison of my reference position versus my position of my device on the test. Now, if I move it in here, so at a certain point I will get a more or less good result. I could also do, looking at the Lissajous figure, I go outside again. So you can easily see how the signals come on here. And so at a certain point I get a figure. I fix it now. So you can easily see that I did not reach my target amplitude, which is a 1 volt signal. And there's also some offset. So this is not centered. But now with a special piece of AI software, I mean an all-inclusive software, I can do this calibration including our front-end chip. And that's what I can do here, pushing a button. Commissioning is finished. Maybe you don't trust me. Well, we are all VisiBig engineers, and that's why I got some nice tools to check what we did. Let me zoom in here. Oh, wait a second. I will switch back to the analog Lissajous figure just to show you what happened now. So I got my target amplitude, more or less, and the raw offset has been compensated. So now I have a signal which can be easily processed by our signal processor. And how does this perform? Well, I switched my scale here, and now I have these red bars indicate 0.1 degree in total error. Scale is here 1 turn. And now if I switch on AGC and dynamic error correction, I'm ready to add alignment errors. For instance, let me tune up the x-axis, z-axis. So this knob does 500 micron per turn. So I'm turning it up. So we get more noise, of course. The sensor signal is getting weaker, needs to be more amplified. I go the opposite direction. That is 0 again. And now 500 micron closer to my target. Well, I can see that now it is getting more harmonics. So here, this design plays well if you are away from the target. I reset it to my initial position. Here. And now I move the sensor in a XY range. This control does 250 micron per turn. So I go 1 turn. It stays within our error bars. I go back. And I go back in the opposite direction. Again, no large changes. I tune it back. So finally, I'd like to demonstrate you the AB jitter performance, and that's where we are using the picoscope here. Let me switch it to 2500 CPR, and let me trigger on an AB signal, and let me zoom in. Okay, now this now tells me a word about the jitter, or the edge jitter over several revolutions here. So we have 8 digits for one period, meaning that when I'm here within less than a half digit, I have a jitter performance which is better than plus minus 6% or so. And I can promise you, finally, this system is good enough to perform better than plus minus 5%. Okay, let me switch back to my presentation. So we've seen the sensor system is quite easy to install, and it's accurate if you compare it to Hall sensors, of course. Low latency, low hysteresis. The hysteresis point is something, if you have noise on the sensor, you need it to keep the incremental output quiet. Here we have a very good signal. We can work with very low hysteresis. Stray field immunity is an intrinsic thing due to the symmetrical antenna and, of course, our active filtering. The sensor itself, it's temperature stable in its sensitivity, so we are not losing signal if you go higher temperatures. And, of course, costs, the targets are quite cost-effective. It can be made of a small piece of metal or PCB-based coils. Space requirement, if you compare it to the resolver, that's easy to say. We are smaller. There's a synchronous output as an option. And I can foresee that this approach is suitable for any application: speed, torque control, positioning, robots, of course, automatic guided vehicles, vending machines, and so on. Now, one word about the tools we are going to have. We are going to offer you, so there will be a front-end PCB having the GI22 on it, so you can easily exchange the sensor coils. The breakout board here offers all the connectors and also the pins where you like to inspect the signals, and it provides the connection to an already existing evaluation board, the TW29-4D. So this is equipped with the MCU we are using here for automatic conditioning. Now, I'm at the end and now ready to take your questions.
Joachim, thank you very much. Very interesting to learn about the new inductive sensor. So just for the audience, I noticed a few people have to leave this presentation, but this is recorded and we will take all your questions, and Joachim and I will have at least 10 questions to answer now. Plus, if you have follow-up questions, you could always contact iC-Haus and Joachim in particular via email using your usual contacts. So without further ado, Joachim, I will start with our questions. So the first question is, what are the minimum and maximum diameters for the absolute trays?
For the absolute trays? Okay, that's a good question. I can foresee that we hardly should go smaller than 20 millimeters. So we are not competing with the on-axis Hall. Those components are the smallest ones. Okay. And for the larger diameters, we already checked something with 80, 90 millimeters. So this generates a very excellent 1 CPR track, the absolute track. Beyond that, we are going to evaluate this. We have some good ideas how to solve those tasks.
Good, excellent. Thank you, Joachim. Next question is redundancy or functional safety a possibility with iC-GI22?
So the GI22 is our very first product, so we did not yet design it under the aspects of functional safety. Of course, you may have noted that we included typical functions required to check if the sensor is alive and working in a good condition. And with the sine-cosine output, you are free to inspect this on side of the PLC as it is traditionally done with when you do analog safety things. Okay. We are prepared, but so far it is not a safety item to any regulation or so.
Okay, thank you. So the next question is, what resolution is achievable if you only use the absolute slave signal for interpolation?
Resolution doesn't help us anything. Likely accuracy is meant here. So we have seen it's a question of the sensor size. If you have a larger diameter, you can easily get an accuracy of about 8-bit. And this is what I would foresee as a limit, as a useful limit for the 1 CPR track. I did not mention, by the way, the sensor does not know what's in front of it. So if you change the scale via non-your system and put in 16, 15, or maybe 64, 63, it can also process this. It just makes the evaluation circuit more complex.
Okay, good. Okay, let's move on with the next question. Were offset and phase also automatically controlled during the operation like amplitudes?
Yes, correct. Not on the front end. There's no offset control, so that's why we measure it. That's why we align it once. But then the dynamic error correction of the signal processing is taking care of changes, including the phase. Okay. But so far what I've seen is that phase does not change a lot.
Okay, good. Thank you. So let's move on with the next question. Is the battery mode with pulse TX coil excitation possible for this?
Maybe. So we didn't check this out yet.
Okay.
The energizing it's not too much energy. We also like to keep this excitation energy as low as possible, since this can cause radiation and you may be in an environment which does not allow radiation.
Okay, good. Okay, let's move on to the next question. We have quite a few actually coming up. So, does movement velocity between the target and the sensor signal affect the sensor signal? So does a faster rotating target generate heavier or lighter signals on the receiver coil?
Velocity doesn't play a role. I did not yet demonstrate it here, but I could easily speed up my drive up to 5,000 RPM or higher. So the accuracy reading stays stable. What I may get are some resonances from my drive.
Okay.
So
Good.
this comes visible.
All right. Good. The next
Mechanical
question.
resonances.
Yeah. Okay, thank you. So the next question is, GI22 suitable for automotive applications? Has the iC-GI22 been developed according to the ISO 26262 standard?
No, it has not.
Yeah. Okay. That's a quick and clear question, answer, sorry. Next question is, can the inductive solution provide more immunity from EMI and magnetic fields in comparison to the ICMU?
Yes, I would say so. Imagine if you have disturbance fields. So all the Hall sensors are working in a low frequency range. So chopping is below 1 megahertz or so. They have to deal with low frequency signals. Not so here. I did not point out this. We have a very high frequency where we run in. So this receiver coils, they filter out everything what is outside our frequency range.
Okay.
So they focus on this 2 to 5 megahertz range. Everything what is lower frequency is filtered out. Now that is why we have an excellent stray field immunity here.
Okay, that's good. Okay, no, thank you. Next question is, what is the typical air gap from rotor to PCB coil?
Yes, that depends on the sensor design, exactly how many metal segments you have on it. So here that is extreme, 2.5 millimeters, but targets having 8, 16 or any other number, they will reduce the air gap. For instance, I evaluated a target with 16, so air gap is 1 millimeters. And then, of course, the tolerance for the Z movement also reduces to a few tenths of millimeters.
Okay, good. We've quite a lot more questions, so we'll just push through. And we have the next question is, for basic incremental applications, can a simpler interpolator be utilized without a hosted microprocessor like TW2?
Most interpolation ICs do not feature this dynamic error correction. And I would say it's a must-have.
Okay.
So TW28 would be an option, TW8 could be an option.
Okay.
They will perform as good as this IC here.
Okay, excellent. Thank you. Does the built-in self-calibration of GI22 have the same performance as TW29?
Not quite. So the calibration range is allowing you to trim the outgoing offset below a millivolt or so. The accuracy of the single processor is more on the 12, 13-bit range, 12-bit range.
Yeah.
So this is means that we trim below 1 millivolt.
Okay. Good, thank you. So what would be the typical temperature range of this sensor to operate in?
I did not mention this. So this system can play -40 up to 125.
Okay, good. Excellent. What are typical assembly tolerances for this sensor?
That's the question of the scale design. The sensor design, how narrow you are placing the tracks and also the diameter, so this determines this. It's not related to the GI-IC. So,
Okay.
what I demonstrated here is that what we like to have, and I've also seen that the larger targets, they give you more space, so it's more easy to have more alignment tolerance.
Okay, good, excellent. So how does the accuracy look for linear systems, and what is the minimal width for linear systems here in this application?
Minimum width, maybe around 5 millimeters or so. travel length I would expect at least if you do this target what I have now in rotary form factor. If you do it linear, you are 100 millimeters or longer. Maybe also 200 millimeters is possible. So that is the range we are in.
Okay, thank you. So the next question, would it be possible to stack the absolute track on a second layer and use different oscillator frequency to save space?
That's an intelligent question. Let me talk to our engineers on this and get back to you by email.
Excellent, okay. You talked about 14-bit accuracy. Do you mean noise-free resolution at this point, since the accuracy would include the mounting error?
The mounting error, you need to remember that the scanning is holistic. So our receiver coils look globally at the target, so the mounting does not change a lot. So it does not change the total harmonic distortion of our signal.
Yeah.
So this does not play an extremely important role. Okay, if you would ask for maybe 10 arcseconds in accuracy, then it's physics. You need to take care of everything.
Yeah.
But here for this system, we are not in this range.
Okay, understood. So next question is, if I use a 26 millimeter outer diameter PCB as a stator, how many sine-cosine cycles can I design on the PCB?
Yeah, I don't know it yet. It could be that it's limited to 4.
Yeah.
Maybe more is possible. So we did not yet design such a target. We are going to, but I don't have the numbers yet.
Okay, excellent. Next questions. Are there any points we need to be aware of when replacing the system from a magnetic type to an inductive type?
Sure, everything. Magnetic type, that's not very specific on axis, off axis. So there are many topics. I try to cover everything.
Yeah.
But that is a sophisticated question.
Okay, good. We'll get back on that one. Thank you. Is there any lower power consumption mode to maintain the multi-turn function?
No,
Okay.
that's not intended.
All right. Next question. For linear encoders, is it possible to have cylindrical targets instead of PCB-based coils?
Yeah, I'm not the expert on this coil design, but my feeling is why not?
Okay, good. Moving on. Will iC-Haus support the design of the PCB coil design?
Yes, correct. The sensor design is the most important job to do, especially when you ask for a certain accuracy. We are preparing for this to offer a contracted design, so it is likely that we can start with it in Q4 this year.
Okay, good.
We will have maybe 2 or 3 sample designs we provide with the evaluation boards, but beyond that, it will be due on a contracted basis.
Excellent, thank you. Next question, can we use this product with the 64-63 coil design?
I don't see any reason why that should not work, but I did not have those targets already in my lab.
Okay.
So I have to be careful. Some customers tested it already. They say, oh, it's difficult. Well, I did not do that so far, and
Understood.
Basically what I've seen, the numbers, the accuracy numbers I'm getting here allows it.
Okay.
But maybe we have to check it.
Okay, good, excellent. Just a few more questions. Does the receiver PCB have to be empty, or is it allowed to be assembled?
Populated. Okay, if you place another metal very close, you can imagine that also some more induction currents can be caused. So usually I would say any other disturbance should be away more than the air gap I'm running. For instance, if I have 16 CPR, play 1 millimeter air gap, it would be okay that everything, other electronics are 2 millimeters away, so this is okay. Directly on the back side could work.
Yeah.
So if the PCB has a certain thickness, maybe 1 millimeter, so you are away,
Yeah.
could work.
Okay, good. I see I have another 3 questions, so let's move quickly through them because I know we're running over time, but it's good to have this interaction discussion with you. So does iC-Haus provide TX/RX coil PCBs or only the GI22 chip?
No, we are selling the IC and not the PCBs.
Okay.
We share the designs, yes, but
That's up to
doesn't
the
make
customer.
sense that we ship PCBs.
Yeah, that's up for the customer. Okay, good. No immunity or no change of sensor accuracy against this misalignment of rotating target, question mark. Is there any immunity or change?
Did not understand this question.
You can read it. No immunity or no change of sensor accuracy. Is there any immunity for misalignment?
Yes, that's what I explained due to the holistic scanning.
Yeah.
It's pretty much immune. We have the tools here to inspect this in the very detail, to look at the harmonic distortions. You are welcome to visit us at the upcoming exhibitions. So we will have this demonstration with us. You can do your own things, evaluate it, and then you can carefully check what's happening if you overrun it.
Okay, good. Then the last question, could you use this type of technology to replace a resolver leaving aside the harsh environments of high temperature?
Well, the main advantage of the resolver is still that it is completely without any electronics. It's just coils which are placed inside the motor. Here we must have the IC very close to our receiver coils.
Yeah.
So this may not be as robust as the resolvers are.
Yeah.
But why not? The IC allows the highest temperature range, and also optical encoders which are mounted on the motor, they have to take a high temperature range.
Yeah.
So that is not so different here.
Okay. Good. That concludes the question and answer session. So thank you all for your very good and interesting questions. And should you have any more questions, feel free to forward them to us. We will communicate with you over email. And as Joachim already mentioned, iC-Haus will be at Sensor and Test in Nuremberg in mid-June. And we will demonstrate GI22. So if you are happening to attend, please come by. Myself and Joachim and our other colleagues will be present, and we look forward to seeing you there. And as a final note, thank you very much for a good interactive session, and thank you, Joachim, for excellent presentation.
Thank you for your interest. Bye-bye for now.
Bye-bye.
iC-Haus. Integrated circuits.